Topic 1.5 is titled Polynomial Functions and Complex Zeros. So again, some of this is going to be review from Algebra 2. Should sound familiar, maybe you forgot the details and that's okay. I'm going to teach it like you've never seen it before. The first vocabulary word of the day is the zeros of a polynomial function. Now we've kind of talked about this earlier in this class. The zero of a polynomial function is where the graph crosses the x-axis. So the other words we can use for a zero of a function is also the root or the x-intercept or the solution. But basically we are looking for where that function is equal to 0. That's called a zero. If a is a real number, so the number that the x value where this 0 output value occurs, then x equal to a is a 0 or solution, and we automatically know that x minus a is a factor of that polynomial. Noticing first that if a is positive here, that we would use a negative in the factor, which meant if a is negative as a solution, we would use a plus sign in the factor. Now, if we just look down here, we have this function. How many times does this graph touch or cross the x-axis visually? I see 1, I see 2, I see 3 times this graph visually crosses or touches the x-axis. So if we were going to list out the unique zeros, or the different zeros of this function, we would have a 0 at x equal to -4. We would have a 0 at x equal to -1. And we would have a 0 at x equal to 3. Does that make sense to us? Like those are the locations where that happens. But what I want us to also do is kind of think ahead. And would you say the options are going to be passes through or bounces off? When we're looking at this particular 0, the one right here, would you say that this graph passes through the x-axis at -4 or bounces off the x-axis? Passes through. So let's just write this down. It passes through. How about at -1? Does it pass through or does it bounce off? Passes through. But what's happening at 3? It bounces. So there's going to be a difference. I spelled that word real funny. Let me try that again. There's going to be a little bit of a difference. I spelled it wrong again. Bounces. In how the zeros behave along the x-axis, and really these are our two options on it passing through the x-axis, going from negative outputs to positive outputs, or just bouncing back. It's called being tangent to the x-axis, but we can think of it as bouncing back. And the reason that's important is twofold. If you notice, I didn't even read this part. Here's the function that's actually graphed. What do you notice about the values inside the parentheses here? They change signs. So exactly like we said in the little top here, since we had +4 as a factor, we have -4 as a solution. Because we have +1 as a factor, we have -1 as a solution. And because we have -3 as a factor, we have +3 as a solution. Do you notice something that's similar between the factors that we both wrote the word passes through next to versus the one that we wrote bounces next to? Good observation. Is there anything else that we see? Maybe if I highlight the things I'm wanting you to see, you might see it. Squared and cubed, and then the one that doesn't have a number showing, what is that number? 1. Okay, so if there was a 1 right there, what can you tell me about the numbers that gave me a passes through versus the numbers that gave me bounces? These two numbers are what? Odd, and this number is even. Interesting. So there's something to do with the powers of those factors. And the thing that happens with the powers of the factors is called the multiplicity of those zeros. So when I'm talking about the multiplicity of a 0, I'm basically talking about how many times does that factor or that 0 repeat. If a linear factor, x minus a, is repeated n times, then the corresponding 0 has a multiplicity of n. So we're looking for the degree, essentially, of its factor. I think that's like an air quotes on the word degree, but you can think of it like that, kind of like the degree of a polynomial, right? The degree of its factor is the multiplicity of that 0. And there is a rule here that says for odd multiplicityed factors, the graph of the function passes through the x-axis at that 0. So we go from negative outputs to positive outputs, or positive outputs to negative outputs. And even multiplicity, on the other hand, I'm not going to write the word bounces here because I'm going to give you the formal definition, but the graph of a function is what's called tangent to the x-axis. It does mean bounce in practice, but being tangent to something means you touch it and go away. One touch, that's it. So we bounce, we come back. That's called being tangent to something else. So if we looked here, the powers of these factors exactly told us what was going to happen in the picture. Since the power of the x plus 4 factor was odd, that means that this is going to pass through at 4. It's odd. Since the power of the x plus 1 factor was also odd, it passes through. But since the power of x minus 3 was even, it bounces back. It's tangent to the x-axis there. So multiplicity tells us a lot of information about the behavior of our graph at their zeros, which is pretty cool. So one of the things we're going to have to do here is we're going to have to list out both the zeros and the multiplicity of those zeros to start to understand the real behavior of these polynomials. So for example, we're going to state the degree of the polynomial in total, find all the zeros, and state the multiplicity of each zero. So sometimes it's easier to do the degree actually last. Let's save it for a second, and let's do the multiplicities of the zeros. First things first, there are 3 x terms here. We have the first factor, the second factor, and the third factor. The first factor, if we were to solve it, would be 0. The reason it's 0 is because there is no number added or subtracted to that 0. It's multiplied by -2, don't care. If it's not added or subtracted to anything, the x value is 0. How about for that middle one? What is the solution? -1. And how about the last one? +4. Fabulous. It looks like our degree of our polynomial might be 3 because we have 3 zeros. However, if we look at the multiplicity, what is the degree of the term that gave me 0? 3. What is the degree of the term that gave me the -1? 1. And what is the degree of the factor that gave me 4?
2.
Multiplicity 2. So interesting here, since we have a 0 with a multiplicity 3, a 0 with the multiplicity 1, and then a 0 with the multiplicity 2, how many, when we add up our multiplicities, do we actually have? 6. Our degree of this polynomial is actually 6, which is crazy because you wouldn't have seen that right away. You're adding up the powers of all the factors to get the degree. So a shortcut, now that we've seen this out loud, is if you actually show, wow, I cannot write a 1 that's not crooked today. If you actually add up all of the powers, see how it's 3 plus 1 plus 2, we got 6. You can work this problem either way by knowing the degree first and making sure your multiplicities add up to that number, or vice versa, finding the multiplicities and adding it up to the degree. Can we see another one? This one is a little bit more complicated because it's not fully factored. This one was fully factored, meaning there was no x squareds inside parentheses with plus or minus behind it. I know there was an x cubed, but again, no plus or minus. There is some pluses and minuses behind my x squareds, so problem, we have to factor first. Have we factored in this class yet? I'm getting my dual credit in this class mixed up together. No. In Algebra 2, did y'all learn guess and check, or did you learn X puzzles? Guess and check, a little bit of both, it sounds like. Okay, I prefer guess and check because it takes like 0 paper space, especially for a equal to 1 functions, which this is. So if I was factoring just this first guy, okay, x squared minus 4, I would set up 2 parentheses and put an x in the front of each of them. I'm looking for numbers that would multiply to -4 and add to 0 because I'm missing my middle term. What are numbers that multiply to 4 that would add to 0? 2 times 2, right? If one of them's positive, one of them's negative, 2 plus negative 2 is 0. So that means we're going to have a positive 2 and a negative 2. Okay, we factored the first guy. If we take the trinomial next, x squared minus 6x plus 8, and again, we set up 2 parentheses to prepare ourselves, we're thinking of numbers that multiply to 8 and add to negative 6. So let's go with numbers that multiply to 8. Let's just list them out. What are all the numbers that multiply to 8? 1 times, 2 times. Is there anything else? No. Can one of those things add up to 6? 2 and 4. If they're both negative, they'll be negative 6. So boom, we have our factored version of this polynomial. Now that it's in factored form, we can see that there's a repeat right here. Do y'all see that? How else could I write that so I don't have to show that repeat in the middle? X minus 2 squared. So if I rewrite this so that the unique factors are showing, it could simplify down to something like this. X squared, x minus 2 quantity squared, and x minus 4 all multiplied together. Now that we have it in factored form, we can do what we did in problem A, which was list out the zeros and add the multiplicities up to get the power of my function, get the degree, sorry, of my function. So what is the first 0 that you guys notice from this first thing? Negative 2, very good. Okay, so we have x equal to negative 2. What's the next 0? Positive 2, and the last 0? Positive 4. Let's go back and do multiplicities. What is the multiplicity of the 0, negative 2? 1, very good. So would that bounce or pass through the x-axis? Pass through. What is the multiplicity of the 0, 2? 2. Would that bounce or pass through? Bounce. And then what is the multiplicity of the 0, 4? 1. Would it bounce or pass through? Pass through. Fabulous. Okay, so if we're adding this all up to find the degree of the function, what would be the degree of this polynomial? It would be 4. Now this makes sense to me as well, because if you look, we have x squared times x squared, which would become x to the 4th power if we were distributing this. So that double checks for me as well, if we add up all of the powers of the leading terms. Do y'all remember learning about multiplicities last year, at least vaguely? You can say no, that's okay. Multiplicities, it's the number of times the factor repeats itself, or the 0 repeats itself. Now, something you might actually remember from last year is that if you have a picture like this, how many real solutions does it have? Notice I said real. Remember, real solutions are found on the x-axis. How many times does this cross the x-axis? None, but if it's a quadratic, which this is, we know that there has to be 2 zeros. So every once in a while, you will have a polynomial that has roots or zeros that contain the imaginary number. So this one would have no real solutions, but 2 imaginary solutions. You can't see them on the graph, so we can't just look and pick them up. You will have to solve for them. So this picture right here is of the quadratic x squared plus 1. What we're going to do is we're going to set x squared plus 1 equal to 0 and solve for x to find its solutions. To do this, we would subtract 1 from both sides. We get x squared equal to negative 1. How do you get rid of a square? Square root. Now, the thing you need to remember with square roots is you do have to put plus or minus in front of a square root whenever you are taking a square root. If it's a part of a problem originally, you don't have to do that. But when you're taking the square root, plus or minus 1. Or, sorry, put the plus or minus sign. Does anyone remember what the square root of negative 1 is? You can say no. No, okay, great. So the square root of a negative number doesn't exist. So mathematicians created what's called the imaginary unit, and it's the letter I. Now I recommend when you're writing an I that you make it kind of curvy like I just did, so you don't accidentally think it's a random stray mark. But this right here are the 2 solutions, positive I and negative I, for this quadratic. If you notice, we have 2 solutions, the positive and negative version of I. Because it's a quadratic, degree 2, there should be 2 zeros. They're just both imaginary. In fact, all imaginary roots do come in the pairs. And if you have one of the imaginary roots, a plus bi, then so also you have a minus bi as the other root. You have to change the sign of the imaginary part. Like plus and minus I, you should always have two solutions that are complex when you have an imaginary answer. These are called, here's another vocabulary word for today, conjugate pairs or complex conjugates. So let's see if we can just make sure we understand this concept of how to find the complex conjugate. The first two are going to be very simple. If I give you positive 4i, what is the conjugate pair for positive 4i? Don't overthink it. Just change the sign. Negative 4i. So if I give you negative I, what's the conjugate for it? Positive I. Very good. Now here's where it gets complicated. Not really. Don't make it complicated. We're changing the sign of the imaginary part. If I give you the complex number 2 minus 3i, you're only changing the sign of the complex or the imaginary part. So what would be the complex conjugate? 2 plus 3i. Very good. Now what about that last one? If I give you negative 4 plus 2i? Minus 2i, yes. You're just changing the sign of the imaginary part to see that there's a complex conjugate. And the reason we bring this up is because we being math teachers, textbooks, test writers, like to remind you that, or like to see if you remember that complex conjugates come in pairs. So when it comes to giving you one of the zeros that's complex, you have to know the other one is automatically assumed to be there as well. So I won't tell you both, you just have to remember that one means both. Now, this all leads us to what's called the fundamental theorem of algebra. And you're probably thinking, I've been taking algebra classes for like 16, 17 years. How are we just now getting to what's called the fundamental theorem of algebra? I know, but it's actually very simple. The fundamental theorem of algebra says that a polynomial of degree n has exactly n complex zeros when you start counting multiplicities. So just like in those examples before, when we found the degree of the polynomial was 6, it was because there were 6 multiplicities when we added them up. That's the fundamental theorem of algebra. It allows us to then take a complicated question like number 3 and very easily answer it. Number 3 says the graph of the polynomial function f of x is shown in the figure on the right. It is known that x equal to I root 3 is a zero of the function. Wrong color, Miss Quigley. This is one of the zeros. I gave you that information. Your spidey senses should be going off because if I root 3 is a 0, what do you automatically know is also a 0? Negative I root 3. Yeah. Change the sign next to the I. So we automatically know, right? They tried to trick you by giving you one of them. You have to know the other one exists. The question asks you, what is the least possible value of the degree for this function? Here's how we answer it. Based on the picture, what are the zeros of this function? Negative 1 and 3. Okay, cool. So the zeros of this function occur at x equal to negative 1 and x equal to 3. We also know that the zeros are at x equal to I root 3 and at x equal to negative I root 3 because it gave us that information in the problem. Just right here, how many zeros did you write down? Sorry, of all the zeros, real or imaginary, how many did you write down? 4. It's very tempting to say that 4 is the least possible degree of this polynomial, but that's wrong because we have to count multiplicities. If we remember to look at the graph, at x equal to negative 1, does it bounce or does it pass through? It bounces because it bounces, and at 3 it passes through. We know that the 0 at negative 1 has to be at least an even number. What's the smallest even number you can think of? 0 is actually neither even or odd. It's like the only number that's not one or the other, which is kind of cool. What's the next one you're thinking of then? 2. That means it's probably degree 2. Might be degree 4, but it's definitely at least degree 2. What is the least possible multiplicity for 3? Since it passes through, we're going to call that multiplicity 1. The imaginary answer should really always be multiplicity 1 for each unique imaginary answer. In which case, instead of just getting tempted to add up the number of unique zeros you see, when we add the multiplicity, what's the least possible degree of this function? 2 plus 1 plus 1 plus 1 is 5. So you have to count the multiplicities instead of getting caught up in looking at just the zeros you can see. Our next task when it comes to polynomials is to solve the polynomial inequalities. And we're going to start off with the easy ones, which is where I give you a graph. And then we're going to get to doing this analytically, which means by hand. But if we're looking just with a graph, solving a polynomial inequality is not too bad. Because answering the question, where is f of x greater than 0? That's like asking, where is the graph above the x-axis? Because I'm looking for where the outputs, f of x, are positive, greater than 0. If the question switches to f of x less than 0, I'm looking for outputs, or the function f of x that is below the x-axis, because less than 0 is negative numbers. So if we start looking at these questions, and I've already answered them for you, like I typed them in there since this lesson was already pretty lengthy, just so you can see these answers. The first question here for this graph says, where does f of x equal 0? And you've already done this today. You found the zeros. So boom, here are the 3 places where the graph touches or crosses the x-axis at -3, -1, and 3. The questions now might start asking inequalities. So where is the function greater than 0? We're looking for the intervals where the graph or the outputs are positive. Would you agree with me that this section of the graph right here is where the function is positive? What I want you to highlight is highlight the x-axis on that interval from -3 to -1. That's the first interval where the graph is positive, where the outputs are positive. Is there another interval where the outputs are positive? 3 up. Instead of saying 3 up, because I get what you mean, 3 to infinity, because we're looking at the x values. So from 3 all the way off the graph off this number line, headed to infinity, yes, theoretically up, because I get it, but off because we're getting the x values, that's the other places where the graph would be positive. If we switch the question, I'm going to jump to letter D. Okay, I'm switching to letter D. If we skip the question C and go to where f of x is less than 0, we have 2 places where the graph would be less than 0. Here, the outputs are negative, and here, the outputs are negative. So we can highlight those parts of the x-axis to give me the intervals from -infinity up to -3, and from -1 to 3, where the outputs are below the x-axis, where f of x is less than 0. Now, my question for you is, do you see a difference in the way the answers are written from B, which is just greater than 0, to C, which is greater than or equal to 0? What's the only difference there? From how this is answered? The brackets. Do y'all remember that from algebra class? That if you have a closed symbol, meaning a symbol that says greater than, oops, that's not a highlighter, greater than or equal to both colors, then you need to include the actual zeros where they're equal to the x-axis. So we change from using parentheses, which are an exclusionary symbol, to the brackets, which mean include these numbers. So same concept kind of fits for E, where if you look, this time I'm asking where is it less than but also equal to 0. The same interval is used, I just changed the endpoints because I can actually use the zeros of -3, 3, and -1. Visually, do we see what we're doing when we're answering these questions from a graph? Above, below, and equal to the x-axis. You're using the brackets for less than or greater than. Sorry, that's a parentheses in my hand. A parentheses for less than or greater than, and a bracket for the or equal tos. That should feel relatively comfortable. Here's what's going to feel uncomfortable. We've done this with the graph. Here's how we do it by hand. So let's say you don't have a graph. You just have the equation, and it asks you which one of the, or to solve the inequality, okay? Here's what we're going to do. We're going to solve the regular equation as if it says equals. I know it says an inequality, we pretend like it doesn't. We're gonna get the solutions here, or the zeros, and we're gonna set them up on a number line and create a sign chart with the solutions. Meaning, I'm gonna pick a number in the first interval, in the second interval, in the third interval, and in the fourth interval, and I'm gonna pretend to plug it in. I just care about the sign, I don't care about the number. And I'm gonna plug in that number and interpret the sign chart to be able to answer the given inequality. Here's what I mean by that. Here's the first question. X minus 3 times x plus 1 times x plus 4 greater than or equal to 0. I lose this for a second, I'll come back to it. I set the actual equation equal to 0 and solve. Do we understand how I got these numbers? Opposite of the number in the parentheses. I stick them on a number line. It has created 4 sections. Here, 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 and here. I need to pick an easy number to plug in each of the sections. I picked the number -10 to plug in for this section because it's pretty easy to plug in. And theoretically, I'm plugging -10 into this number, and this number. -10 minus 3. Is that a positive or negative number? Negative. -10 plus 1 is still negative. -10 plus 4 is still negative. What's a negative times a negative times a negative? A negative. So we would know that this first section right here is negative. We do the same thing with a number between -4 and -1. I chose -3. You could have picked -2. We plug it in, and when we do that, we're going to get a positive number. When we plug in 0, which is the easiest number to plug in, you're going to get a negative number for the next interval. And lastly, I plugged in 10. You could have picked 4, 5, 1700, whatever you wanted, as long as it was bigger than 3, and I got a positive number. After we do that is when we go back and look at the actual question. The actual question here asked me to find out where the graph was greater than or equal to 0. Meaning I was wanting this section and this section where the graph was greater than, but also equal to the x-axis. So my solution set is the interval from -4 to -1 or from 3 to infinity. Because those are the two that I highlighted in my sign chart. I wanted to work one fully out for you because I know that following the sign chart when it's in your own handwriting, I've taught this class long enough to know that the first one you write down yourself, it's going to be a hot mess. It's okay. You have one printed on the paper to look at again. But we're going to do example 5 together just to practice how to make your own sign chart. Okay, so first things first, we would have to solve the version of this equation that says equal to. Okay, so we set x plus 2 squared, x minus 5 equal to 0. Using the property we learned at the beginning of class, what are the zeros of this function? If it says x plus 2 in parentheses, -2. If it says x minus 5 in the parentheses, +5. So that's it. Those are the only ones I need. I'm going to put them on a number line. I need to pick 3 numbers. How do I know 3 numbers? There's 1, to 3 sections made up here. Somebody give me a number that's less than -2 that's easy to plug in. Give me an easier number to plug in. Even easier. How about -10? Multiples of 5 or 10 are easy to plug in, okay? So we could have gone with -5. You can pick any number you want. I like to pick -10. If I'm plugging in -10, it's like I'm doing -10 plus 2, like I'm plugging it in right here. What is -10 plus 2? -8. So a negative number. I don't really care about the 8 part. I care about the negative. That parentheses is squared. So I'm going to square my little negative sign. If I put -10 right here, what's -10 minus 5? -15. Don't care about the 15, care about the negative. Now we just have to figure out what the sign of the function would be there. What's negative times a negative? Positive. So then I have positive times a negative. This little section would be negative. Okay, can you guys give me an easy number to plug in between -2 and 5? This is the easiest number to plug in, actually. 0. 0 is a very easy number to plug in. So if we plug in 0, theoretically put a 0 right here. What is 0 plus 2? Is it positive or negative? Positive. So I'm going to have a positive squared. And then I'm going to have a 0, minus 5. Is that a positive or a negative number? Negative. So then it's a negative. Positive times positive is positive, times negative is negative. So I'm going to have another negative little section there. Okay. Last one we're plugging in. What's an easy number to plug in that's larger than 5? 10. Yeah. It's just easy. It's just like aggressively larger than usually you're finding your zeros, so it's easy to add. 10 plus 2 is 12. That's a positive number. And 10 minus 5 is 5. That's a positive number. Positive times positive times positive is positive. Okay, whoa, we filled out our sign chart. Let's actually answer the inequality question. This inequality question wants to know where is it less than 0 for this inequality, which means I want all of the sections that were negative. I don't, however, want the zeros because I don't want them to be equal to 0. I just want it where it's less than. So I'm going to put an open circle around my 2 and around my 5 instead of a closed circle around my 2 and around my 5. So if we're actually answering this question, the interval that solves this equation would be from -infinity to -2 and then -2 to 5. You see how the number line gives you the exact numbers you need? Here's a little bonus question though. What if we were solving this question? We got the sign chart and everything like that, and then for this first one, instead of saying greater than or equal to 0 as the question, it says less than 0. We've already done that work, so look at our number line. How would you answer the question if the inequality had said less than 0? Where were my minus signs on my number line? -infinity to 4 or -1 to 3. So two things I want us to look at because we're on the left side here. Those are negative numbers. And do you notice how I switched it to having parentheses in my solution set as opposed to brackets? Why did I switch from brackets to parentheses? So the bracket is used when the symbol has the or equal to sign on it, meaning we can actually touch the zeros. If you don't have the or equal to sign, you have to use parentheses. Okay, so let's apply that to this next one. How would our second question change if the inequality didn't flip the inequality sign? It still says less than, but it says less than or equal to. While I answer the door, I want y'all to try this one. How would you rewrite it if it says less than or equal to instead of just less than? Okay, here's what I'm expecting for you to have written. Don't change what you wrote yet. Here's what I'm expecting to have seen. I would expect, since we added the or equal to, that you listened to exactly what I said and you did this. Is that what you did? So here's the problem with this answer, because thank you so much for following instructions. I did say that if there's the or equal to, you just change the parentheses to brackets. However, do you notice that this is the same number? And that I can include -2 if it's the bracket? So the correct way to actually write this is just with one interval all the way from -infinity to 5. We don't have to take a break at -2 because I can include -2. So you have to take a break at -2 if it's parentheses. You don't have to take a break at -2 if it's brackets, because we're allowed to be equal to -2 with the or equal to part. Okay, picking this back up, what we're going to be doing to determine the possible degree of a polynomial from a table is going to feel a lot like what we did when we did average rate of change on a table, where we found the change, or maybe the change in the change of the table. And because these two tables have consecutive equal length input value intervals, let's highlight that word right there, or that set of words right there, consecutive equal length input value intervals. What I mean by that is, in number order, they're all of equal length on the inputs. For example, from 1 to 3, that's +2, right? What's 3 plus 2? 5. 5 plus 2. 7 plus 2. So they're consecutive. We're not skipping. We're not going out of order, and equal length, all +2s. On the input values, do you see that's the same thing over here on the x's? +3, +3, +3, +3. A lot of times you're going to see them just like +1, +1, +1, +1, like all the numbers. But as long as they're consecutive in order, equal length, input value intervals, we don't have to actually create an average rate of change for the entire table. What we can do is just find what are called the successive differences in the output values. Those are the words right here, successive differences in the output values. You did do this in Algebra 2 at some point, where you just found how many times it takes you doing the differences to determine the degree of the polynomial. So for example, since they're consecutive equal length input value intervals, I don't have to do average rate of change. I just have to figure out the difference between -2 and -3. What is the difference between -2 and -3? I'd have to go down one more, right, to go from -2 to -3. How do I go from -3 to -1? I actually go +2, yeah. So I go +2. How about from -1 to 4? 5. And then 4 to 12? 8. So our rate of change, again, I don't have to do the full rate of change formula because I have equal length input value intervals. I just find the difference here. Are those rate of change numbers for that first degree polynomial all the same? No, so we would skip this one. This is not degree 1 polynomial because those numbers are not all the same. But when I start to do this, how do you go from -1 to +2? +3. How about from 2 to 5? And from 5 to 8? When the change in my rate of change is the same, so change in the rate of change, that means that the second degree here, because I had to do this twice, is probably the degree of my polynomial. So we would say this is going to be degree 2 because the second differences are constant. Or when we were learning this in topic 1.3 and 1.4, we would have said the change in the rate of change is constant. The average rate of change is changing at a constant rate. Or we could say the second differences are constant. Let's see it again, just to see what would happen maybe if it's not similar to a question we'd seen before. We notice on the x values that we have consecutive equal length input value intervals because these are all +3s. So we go to the outputs and we find the differences in the output. How do you go from -2 to 0? +2. How about from 0 to 10? From 10 to 27? And then 27 to 50. 23. Clearly those are not the same numbers. So this is not a linear equation because the first differences are not the same. So we go to the second differences. From 2 to 10, it takes me going +8. From 10 to 17, that's +7. And from 17 to 23, that's +6. Are my second differences the same? No, but if I go one more, from 8 to 7 is -1, from 7 to 6 is -1. Since my third differences are the same, I had to keep going till I get all the same number. We can draw a conclusion that this is going to be a degree 3 polynomial because that third differences are constant. So our rate of change is not constant. Our change in the rate of change is not constant. But the next successive difference is, it doesn't have a cool name. It just is the third differences. But we could pretty much guarantee that this would be a cubic function. If we had to go all the way to the fourth differences, it would be a quartic function. If we had to go to the fifth differences, it would be a, wow, I just lost the word. Actually, it doesn't have a name. Fifth degree polynomial. Okay, I think I'm juiced up enough to not stand in the back because I hate standing back here. Okay, the last topic from 1.5 that we needed to go over is determining whether functions are even or odd functions. And I'm not talking about even or odd functions like numbers. Clearly we know what even and odd numbers are. Even numbers are divisible by 2 and odd numbers are not. But even and odd functions have a different property. Even functions are said to be symmetric over the y-axis. So if we look at this particular function here, it's even because if I highlighted my y-axis and then folded the graph on that y-axis, do you see how one side would fit exactly on the other? That is symmetric over or about the y-axis, and we would call this an even function. If we were solving this analytically, meaning by hand without a graph, what we would do is we would plug in a -x to everywhere in the function that there was an x. We would then simplify as much as possible, so squaring some stuff, multiplying some stuff, adding if possible. And if you end up with the exact same function that you started with, that is an even function. So even is the y-axis. You get the same function when you plug in a negative number, because we're reflective over that y-axis. An odd function, on the other hand, is an odd function, oh, sorry, I said those words twice, is a function that is symmetric about the origin, which is nice because odd origin. Now what this looks like is not a fold. In my mind, this is like a rotation. So if I were to put a pin in the origin, meaning like hold this function down on the origin, and then rotate it around. Do you see that this side would land right on top of this side if I rotated it? That's an odd function. So it's a spin. Put your finger right on the origin and flip your paper around. It will look the exact same. Odd origin. To find this out analytically, what we're going to do is still plug in a -x value. But instead of getting out the exact same output, we should get out the opposite. Every single sign should change in that function so that it is all the opposites. Odd, origin, opposite. It's so nice when things work out that way. Odd, origin, opposite. So let's see what this might look like, finding these analytically and graphically. And in fact, we're going to do the graphically ones first. So if you look at your questions down here in example 7, we're going to skip A, B, and C, which I've started for you. And we're going to look down here at D and E. We're just trying to determine whether these are even, odd, or neither. Can I, maybe don't highlight this because I can erase my highlighter. Can I fold this graph along the y-axis and one side land right on top of the other? So this side right here would fold right on top of the other side? No. So this one is not going to be symmetric about the y-axis. Let's check if it's odd, meaning symmetric about the origin. If I put a pin right here, and then I spin my paper around, would one side look like the other side? Yeah, this is going to be odd. And if you don't trust me, I actually do the spinning thing. This is really hard for me to show on my iPad because when I spin it, it doesn't spin it on the TV, but watch on my actual iPad. If I put a pin right there, you see the shape? And it's going to rotate, so don't let it rotate. Does it look the same before it rotated? Yeah, that's an odd function, okay? That's an odd function. Now, if we look at the second graph here, we have to ask ourselves the same questions. If I folded it on the y-axis, would it perfectly fold in half? No, so it is not symmetric about the y-axis, it's not even. If I put a pin in the origin and rotated it this direction, would one side land on top of the other? No, so this one is neither even nor odd. In fact, most functions are neither because it's a very specific type of function that can be even or odd. Most functions we deal with in real life / in this class are going to be neither because it's very, very specific when we get an even or an odd function. Well, let's see what this looks like analytically because we did skip some questions here. It asks us to determine if these are even, odd, or neither, but it only gave us an equation. And just like today you didn't pick up your calculator, oof, because we can't do this one with the calculator, we're going to do this one on our brain. So like I said in the examples up at the top, what we're going to do is plug in negative x. Do you see how in the part I've typed for you, everywhere there was an x a second ago, I've put in negative x. Okay, let's evaluate. What is a negative times a negative times a negative times a negative? That's 4 negatives. Let's do that slower. What's a negative times a negative? Times a negative? Times a negative. We're back to being positive, right? So this first term would be positive 2x to the 4th. For this second piece, I'm going to square negative x. What's a negative times a negative? A positive, but then I have this little negative in front. Negative, so then I'm going to write down at negative x squared. Nothing happens with that plus 5, so I drop down the plus 5. My question for you is, even though we plugged in a negative x, didn't we get visually the exact same equation we started with? If we get the exact same, that's an even function. Because, and let's use a definition so we get used to seeing this, because h of negative x, when we plugged in negative x, looks the exact same as the original function h of x. So if you plug it in and you do all this work and nothing changed, even. Let's see one more. Again, I started this one off for you. Everywhere there was an x in the k of x function, I have put negative x. Let's do this bit right here. What is a negative times a negative times a negative? Negative. So negative times negative is positive. Times negative is negative. So this first little bit is going to be negative x cubed. 3 times negative x, what should I write down? 3x, and then nothing happens with the negative 1, so I drop it down. Now we compare. Is what we ended up with the exact same as what we started with? No. Interesting, so it's not even. Is what I ended up with exactly the opposite of what I started with? Yes. Are you sure? No. Every single sign has to change to say it's the opposite. Did every single sign change? The first one did, the second one did, but did the third one? No, so this is actually neither even nor odd because, ooh, that's a weird looking because, let me spell that better. Because the k of negative x does not look like what it started with, nor it does not look like the opposite of what I started with, which are the two definitions of even and odd. That's fancy math talk for it doesn't look the exact same and it doesn't look the exact opposite. every single sign has to change for it to be the exact opposite. Last one. Probably can guess what this one's going to be, but here we go. Okay, so I took j of x and I plugged in a negative x everywhere there was an x. Ooh, we're doing to the 5th power. We'll do it slowly. What is a negative times a negative? Times a negative. Times a negative. Times a negative. Okay, so this first term is negative x to the 5th. Great. What should I write down for the next term? Plus 5x, right? Because a negative 5 times a negative x is positive 5x. Okay, question. Does this look exactly like what we started with? Does it look like the exact opposite of what we started with? Agree. Since it looks like the opposite, we're going to call this an odd function. And it's odd because it fits the definition. J of negative x is exactly equal to the opposite looking j of x. Odd opposite. And that's opposite every single place.